Hi friends, welcome to the channel Learning R is Fun. In our last video, we have covered multiple linear regression, and in this video, we will be covering logistic regression. In situations such as US election, wherein you have to choose between one of the two candidates. So this is a case of logistic regression. That is, you have a number of factors, but ultimately using these factors, a decision is to be taken. Either it is Mr. Trump or Mr. Biden. So the dichotomous outcome variable, that is Y variable, can be either male or female or pass or fail, etc. Whereas the X can be any number of factors. You can say they are the predictor variables. Normally, Y will be written as a linear combination of the factors or the predictors. Say Y is B naught, beta naught plus beta 1 X in the linear model. In the logistic model, instead of equating beta naught plus beta 1 X to Y, we just equate this beta naught plus beta 1 X to log odds of the Y. What is this log odds of the Y? That's what we will find out in the next slide. Before that, let us have a look at the chart. In the normal linear regression, you have a blue line. The line crosses the value 1 and 0, and it can be anywhere. That means this value can be, Y value can be anything in the minus, or it can be plus of any magnitude. Whereas in a logistic situation, we want either 0 or 1 to be the Y. So if you see the other curve, which is looking like S, that is touching either 1 or 0, or it is very close to 0 and 1, which is neither it is touching 0 or 1. Because a prediction, generally it cannot be perfect, therefore it will not touch 1, it will not touch 0, but it is very close to each. So in order to have a conversion of the Y value, which is normally of any magnitude, to the magnitude of 0 to 1, we need a function, a mapping, and that mapping is the logic function. How this mapping is done is what we will see in the next slide. So we have to understand first what is probability and what is odds. Suppose A and B play matches, 8 matches, A wins 5 times. Then the probability of A winning, we can say 5 out of 8. The probability of A losing is 3 by 8. Okay. Now, we can say odds of A winning as 5 to 3. That is 5 times win versus 3 times loss. So 5 by 3. That can be said as odds. When you say probability, you say the total wins, total matches in the denominator and number of wins in the numerator. Whereas in the odds, the favorable situation divided by unfavorable situation. That is 5 times win by 3 times loss. So 5 by 3. Now if you see the last but one bullet, the odds can be obtained from probability, and the last bullet you can say probability can be obtained from odds. That is, odds you can say P by 1 minus P. So 5 by 8 divided by 1 minus 5 by 8. It will ultimately give you 5 by 3. That is, odds are 5 by 3. And the probability is 5 by 8. In the last bullet you can see the probability can be obtained from odds. Odds divided by 1 plus odds. Odds in this case is 5 by 3 divided by 1 plus 5 by 3. So if you calculate, it will become 5 by 8. That means you are getting a probability out of odds. So you now understand odds and probabilities are one and the same thing, expressed in different ways, but they can be obtained from one from the other. So when you say log odds of probability, it means logarithm of the odds. So you can see here Y we are representing as the logarithm of the odds. That is P divided by 1 minus P. We take logarithm to that, to the base E, that is a natural logarithm. Now this equation you can just expand, like you can remove log from right hand side and bring it to the left hand side, then it will become exponential. Some maths is involved here. P by 1 minus p is e to the power y. From this 1 minus p you can multiply on the right hand side and then again take p out of that. Then you ultimately get this p as 1 by 1 plus e to the power minus y. Now y is, we know, b0 plus b1x. So what we get here is the logarithm of the odds is now y. Previously it is a linear combination of the factors, but in this case it is not a linear combination of the x variables, it is a logarithm of the odds. So that is the link between these two. To see a real life example, we can take logarithm of the probability of the Donald Trump will win US presidential election versus he will lose. That as the b0 plus beta 0 plus beta 1 into amount of money spent on his campaign plus beta 2 into amount of time spent on campaigning negatively plus beta 3 into his popularity index plus so and so some beta into his effectiveness in combating the voters fraud which he is alleging, then plus beta n star other factors plus white noise. So basically you are equating the log odds of the probability with the linear combination of the various factors. In logistic regression there could be three types. The one which we have discussed so far is binomial, that is either 0 or 1. It could be multinomial or it could be ordinal. In the second case, it could be something like, we know nominal values, categorical variables can be either nominal or ordinal. So nominal means they can be simply some namesake, some names are there, red, orange, blue. There is no order here. Whereas in ordinal, you get order, very likely, likely, less likely, etc. So between these three, we will have to distinguish. Our situation is dichotomous, so we will use logistic regression. To carry out these regressions, we resort to generalized linear models. Now, generalized linear models means there is a linear combination of the x values to get y. And y will follow one of the three distributions, either binomial or Poisson or normal distribution. So these are the assumptions. In our case, it's following the binomial distribution. That's why logistic regression is being used. In the normal linear regression, we have used t-test. Here we will use wall test. Of course, we are not specifically writing any test. It is already inbuilt into the regression GLM function. So we'll have to only say the family is binomial, then we get the results. Now with this background, let's go to RStudio. In today's session, we'll have two examples. One example is familiar, empty cars. So we'll just execute the first statement. What is empty cars? And here we could see a transmission value which is either 0 or 1. This we can take as a y value and we will predict this value based on some of the factors here. So in this case, we will select only cylinder, HP and weight. And then of course the y variable also will take. And these are the variables I am going to pick up from empty cars, and that I am going to make another data frame. So a DF has been created with only 4 variables now. Now let us see some sample of that. We are seeing AM, which is the y variable, which is either 1 or 0. Remaining 3 are the predictors. Now let us do one fit. Here we have to use, instead of LM function, we have to use GLM function, and then we have to mention the family. Here it's a binomial family because we know it's 0 or 1 is the outcome. And we already decided the formula that other 3 cylinder, HP and weight will take, and AM will be a function of that. And AM, incidentally, the transmission, if it is 0, then it's automatic. If it is 1, then manual. Okay, let's do the fit. done the fit. Now let us see the summary. In the summary, there will be difference in what you have seen in the previous linear model and the logistic model. Here instead of residuals, we are seeing deviance residuals. The aim, of course, to get as much less residual as possible. Okay, coefficients, as before we have seen, coefficients also estimate standard error. Instead of the t value, we are getting z value, because we are using a wall test here, and then the values are given in the z, and based on the z value, we are getting a probability. When you look at the probability, we see this weight is a factor which is important, and maybe HP may be important because it's close to 0.05. Of course, cylinder is not useful at all. So this is what we get from this, and of course some other factors are here. Previously we used to get R square and all. Here also it's goodness of fit information. When we say null deviance, that is when you are having no coefficients, cylinder, HP, weight is not there, only intercept is there. In that case you get a null deviance. And as and when you add more and more predictors, you get a residual deviance which will be lesser than that. That is, when you predict better, your deviance will be less. So if you are able to get a proper combination here, the residual deviance will come very close to 0. Okay, now this is what you see from this, and AAC is a criterion which is similar to R square criterion in the earlier one. In the earlier linear regression, we have seen the R square value and adjusted R square value. That is, when more than one predictor variables are there, then you look at the adjusted R square. Here also, when we are having different models, which model is better, we can see from the AAC score. Okay, this is general understanding. Let's predict for a particular example. What we'll do, we'll first redo the model. We'll take AM as a function of HP and weight only, cylinder will avoid, and this will call as AM.LFit2. So now for a HP of 120 and weight of 2800 pounds, here actually 1000 pounds weight, therefore we give 2.8. So HP of 120 and weight as 2.8, what should be your transmission? What is the probability for your transmission to be, in case of manual, to be manual? This is what we are going to see. So first we will wrap the data, then we will use a predict function. In the predict function, we have to give the whatever model we have developed, and then we have to use the new data and then type as response. So you get a prediction here. So we got 64.18%. Here we get a value 0.64. Basically it is 64%. And since AM is 1 is manual, the probability that for this particular engine and 120 horsepower and this much of weight of the car, then you are likely to have a manual transmission is 64%. This is how you get it. Now you can also look at the model summary of LMFit2, the previous code also. Let me use LMFit2, and now you see a residual deviance of 10.059. The previous one, the residual deviance of 9.98. AAC we are getting 16.059. Here the AAC is 70. AAC becoming better, but residual deviance is not better. So this is what you learn from this, and then you start further analysis. Now let's move on to the second example, that is diamonds. Before that, let me clear this. Let's go ahead with the second example. Here we are using a dataset called diamonds. This dataset as well as many other datasets are included in a package called YAR, and there is a book also, that is the Pirate's Guide to R. This is available in the internet, and this package supports all the datasets available in that book. And let's go by loading the package into the memory using library. You have to do the installation first. Then let us look at the diamonds. there are only 4 columns: weight, clarity, color and value. We don't see any logical value column here, but the value column is what we are going to use for the logistic regression. How do we do that? Let's get into the problem first. There is a problem. Predict the probability that 3 new diamonds with values weight, clarity, color, the 3 sets of values have been given, will have a value greater than 190. So based on the weight, clarity and color, a diamond is value and the value is available. Now in this column the values are available, and if you ask a question whether it's greater than 190, then you will get false, true, then you will get false, true again, false, false. So there is a new column which you can create, which will have only logical values. That's what we are going to do as a first step in getting these probabilities calculated. So here what we have done, value.g190 is the new column which will come here, and diamonds is a data set, and here value is available column, and we are asking a question whether it is greater than 190. So for each of these value, that question will be asked and the results will be stored in this vector, and that vector will become a column. Okay. Now if you look at this, then we will see a new column added, which is false, true, etc. We know true means 1 and false is 0. So we can assume value.g190 is our y variable. Okay. Now let's do the fitting. In this fitting, we'll just do first a model without any predictors. That means we will not use weight, clarity and color. We will use only an intercept. So how do you do that? You have to say value g190 is the y value, and for x value you have to simply say it as a function of simply number 1. It means only intercept. Let's do this model first. I'll call this model diamond.lfit0, and now let's look at the summary of this new model which we have created. The summary, we get the formula and then deviance residuals here. Then we are getting coefficient. It is not less than 0.05. Therefore this model is not going to be useful, but for this purpose only I have done this whole thing. Null deviance is 207.52, residual deviance is also 207.52. That means without any predictors these are same. Okay. Now let's go ahead and create a proper model where diamond.lfit will call it, and here we'll say value.g190, the y variable, is a function of these 3, remaining all same. So let's execute this statement. Now let's ask for the summary. In this summary, if we see the AIC value 114.67, in the previous summary it was 209. So we are getting a better model, and here null deviance was same, but in this case null deviance and residual deviance, you can see the difference. As you added predictors, we are getting a better residual deviance. Okay, and you are seeing the coefficients, all 3 are significant. Intercept as well as weight and clarity, they are significant. Of course color is not significant. Here there is no indication, as well as we see the 0.05 should be the probability or less than that, but here we are getting higher than that. So color is not having any effect here. Okay, let's keep the model as it is, and now we'll go for prediction. So what we'll do, in the diamond.lfit, which is a list, you can see here 30, in this there is a member fitted values. For all the values available in the data set, values have been fitted, and fitted values whatever is available, will keep them in the predicted.g190. Okay, so we can include this into the data set. So we can ask now what is diamonds. You can see here predicted.g190, we are getting values here. Let's just look at these values. Here 182.5, and it is less than 190, and you are seeing a probability of 0.16. Here we are seeing 191.2, the probability here is more. When you are seeing less than 190 in a farther place like 175.7, probability is very less. That means the probability of this getting valued more than 190 is high here when it is closer to 190. So 195, this should be definitely better than this. Yeah, we are getting better than this. So you can see like that. 197, but however here we are getting a probability lesser because of the other two factors. Okay. Anyhow, this is what the model understood. Now let's go back to the code for the problem. The problem is saying that there are 3 diamonds with weight 12, clarity 1 and color 5. The second diamond is having values of 6, 3 and 2, 6, 1 and 2. The third diamond is having weight of 5, clarity 1.5, color 3. What will be the probability that the values for this will be more than 190? That's the question. So let us wrap this data into a data frame as usual and call this as a diamonds.new. Okay. Now we have to do the prediction. Prediction can be done straight away. Normally when you are asking the predict function without any parameter except the fit as well as the new data, what you get is the logit predictions. That is the logarithm of odds. So let's go ahead and get it. So logit predictions we have got, and to take an inverse of the logit predictions you have to apply this formula 1 by 1 plus x to e to the power minus logit predictions. Then you will get probability here. So this how this equation is coming about, you can see in the box. There's an explanation given. So I will avoid the maths, but you can, if you are interested, you can take them and then see how this is done. Okay, now we can get the probabilities like this. Okay, and probabilities of predictions can be again taken using another function. Instead of this mathematics, we can use a function inverse dot logit. Then you can give logit predictions. Then you will get the probability of predictions. We'll do that. Now you see these two are here, given here. They are same. So either you do maths or you do this. There's a third way. Here what we can do, in the predict function itself, we can say type is response. If you say type is response, what you get out of this is straight away probability of predictions. So you got the probability of predictions. So now for the first diamond it is 0.99, that is 99%. For the second diamond it is 0.02, that is just 2%. For the third diamond, the probability that it will be valued more than 190 is 40%. That is what we are getting. And how this is 40%, why this is 99%, you can just have a look at the what is called the values, and then you may be able to get an idea. Here the weight is less, here the weight is more. More the weight, the value will be definitely higher. The clarity, the more the clarity, the value will be higher. We are having a clarity of 1.3 here, whereas here is 1.5. The second case, the clarity is very less, weight is also less. Therefore this probability is very less, that is getting more than 190 value. Whereas the first one is having higher weight and better clarity comparatively with the second one. The third one, it is having better clarity, that's why it has come up to 40%, though the weight is less. Okay, color, of course we have seen that it's not having much of a difference, but anyhow we can visualize this and see whether the color is having real impact also. For that purpose we have to load a package called effects. So first install the package, then load it. So the package has been loaded. Now we can do a plot. All effects is a function which is available in the effects package. Like density plot, what we do is plot, within bracket we say density of something. Here we have to say all effects of the model. Model is diamond.lfit. Then you are giving a title. Title is main. We generally give main is equal to effect of weight, clarity and color. So this is what we are going to say, and let's execute this plot. Let's try to understand the plot. First plot, the weights are given here. What are these small dashes? These are the actual values. for the data set of diamonds, you got so many, you can say 150 observations. These 150 observations are all available here. These 150 x weight values are here. And the weights are ranging between 6 to maybe around 5 or so, with that up to 14. These are the weights available. And here the probability is given, value G190. This is the probability that this particular diamond will be valued more than 190. When you look at the probability, you are getting 0.2 here, 0.8 here, whereas this axis is 0 to 1 axis. Therefore, you see this is a non-linear. Y is non-linear, whereas X is linear. That's how the plot has been made. Now, let's look at the blue line. As the weight is increasing, you are seeing the probability is increasing. The probability that it will be valued more than 190 is increasing. The same thing in the case of clarity also. These small dashes are known as a rug plot. The plot is like a rug, therefore this is a rug plot. Whereas here the line says that as you improve in clarity, your diamond is going to be valued better. When it comes to color, the colors have been ordered in such a way, the highest value is for the lowest number of color. Maybe this color is the best color, and when you have this color, the value is better. When you are having not appreciated color, something closer to 8 or so, the value is lesser. So that is the effect of color here. So we can visualize the logistic regression in this fashion. With the two examples, now I am sure that you would have got some fair amount of idea. So let's move on. In the next video, I will be covering time series. Thanks for watching, and bye from me.